So those are some examples of discrete random variables. So let's talk about continuous random variables and some basic techniques for summarizing data from continuous variables. Continuous variables, kind of the definition is that they can assume, in theory, any value between a minimum and maximum. And the key word here is any. The continuous variables do not have to be whole numbers. They don't have to be of a certain form. They can, in theory, take on any value between some theoretical minimum and some theoretical maximum. So continuous variables are quantitative. That means that they take the form of numbers, and they often represent measurements of something. Okay? So as an example, suppose we're looking at the population of patients 50 years of age or older with coronary artery disease. And so to analyze that population, we might go out and get a sample of 7 patients. And for each patient, we measure their systolic blood pressure in milligrams of mercury. And so this systolic blood pressure is a continuous random variable, or a continuous variable. It could, in principle, take on any value between some theoretical minimum and maximum. Now, the minimum, I guess, would be 0. What the maximum is, I don't know, but it's not terribly important. And so here's the 7 different blood pressures that we measured. One patient had a blood pressure of 100, another had 110, and so on and so forth. Now these numbers here are all recorded as integers, or whole numbers, but we have to remember that, at least in theory, systolic blood pressure does not have to be a whole number. It could be a decimal, even though we typically only measure it with whole numbers. And so let's talk about how we could summarize these. And so we're going to first talk about some different sample statistics that we can calculate. The first sample statistic is called the sample mean, and it's denoted x bar. And here's the formula for x bar. This Greek letter here is the capital letter sigma, and in mathematics, capital sigma means summation. So this means that we're going to add up or sum all the data values and then divide by n, which is the total number of data values. So here's our data values. We're going to add those up to get 865. And so then our sample mean is 865 divided by 7, which is 123.6. The next sample statistic is what we call the sample variance, and it's denoted by s squared. And here's the formula for the sample variance. It's a little bit complicated, much more complicated than the sample mean. Now let's talk about what it means and then how we could calculate it by hand if we wanted to. In the Excel lesson, we're going to talk about how to calculate these sample statistics using built-in formulas with Excel. So we're not going to be doing this by hand. We're going to let Excel do all the work. But we should know the basic idea and the basic definitions of how these variables are calculated, or how these statistics are calculated. So the first thing we have to do to calculate the sample variance is to calculate the sample mean, x bar. And then this formula says we're going to take each data value, subtract the mean, square it, and then add all those up, and then divide by n minus 1. So here's our sample data. And the sample mean we just calculated earlier. And so we're going to take each value and subtract the mean. And so for this first value we get negative 23.6. We're going to take this number 110, subtract the mean, and we get negative 13.6. And we just go down the list and do that same for each data value. Now some of these differences are positive and some are negative, but that's okay. Because in the next step we're going to square each one of those differences. So we square the negative 23.6 to get a positive 556. We square the negative 13.6 to get a positive 184. And we go on down the list, we square each one of those values. Okay. So these numbers here are the numbers x minus x bar squared here in this formula. Then we need to add all those up, and we get 22,247. So that's the value of our numerator in our formula. And then the last step is to take that sum and divide by n minus 1. N is 7, so n minus 1 is 6. We take that number and we get 374.6. So that's the sample variance. Now the sample standard deviation is denoted S, and it is simply the square root of the variance. So once we calculate the variance, we just take the square root of that, and so the square root of 374 is 19.4. So that's our sample standard deviation. Now, we don't want to calculate statistics just for the sake of calculating statistics. Once we calculate them, we should take a step back and ask ourselves, what does this mean? It's a good Lutheran question. That's also a good mathematical question. What does this mean, and what do this variance and standard deviation mean? Well, the mean we could think of as a measure of how big the data values are. If our mean is very big, then that means our data values are also very big. If the mean is very small, then that means that the data values are also very small. The variance and standard deviation, we can interpret those as measures of how spread out the data are. And so if we've got a large standard deviation, then that means our data values are very spread out. If the standard deviation is very small, that means that the data values are all pretty close together, so they're not very spread out at all. As we'll see later on in the semester, the variance, or this measure of how spread out the data are, is going to be very important when we talk about estimating a population values. Okay. Now, another way that we can summarize a set of continuous data is to calculate a relative frequency distribution. And this is very similar to a relative frequency distribution for discrete variables, just with a little slight difference. So the basic idea here is that we're going to take the range of data values and divide them into different categories. And then we're going to count the frequency of each category. And so, for instance, let's take the same set of data that we've been working with, and let's use these following categories. We're going to use 4 different categories: 100 or less, 101 to 120, 120 to 140, and then 141 or more. Now you may be asking yourself, where did those different categories come from? Well, there's no formula for calculating them. They're just the categories that we chose to use. And so we're going to form a little table here where the top row has our different categories. Our second row has our frequencies. So our first category, we look at our set of data. We ask ourselves how many data values are in that category. Well, we see only 1 in that category, so we put a frequency of 1. Second category, 101 to 120, we see 2 data values in that category, so we put a frequency of 2, and then 3 and 1. And then we calculate our relative frequencies by taking each frequency and divide it by the total number of data values, which is 7. And then we want to draw a picture of what this relative frequency distribution is telling us. And this picture we're going to call a relative frequency histogram. So we're going to have one column here for each category. And the height is going to be a relative frequency. So you see this first relative frequency of about 0.15, and so on and so forth. And so this picture here helps summarize the data. It shows that the most frequent category is this one here, the second is this one here, and the first and the last have the same relative frequency. Now, one important use of a relative frequency is the shape of relative frequency distribution, and a relative frequency histogram is that it shows us the shape of the data. So what do we mean by the shape of the data? Well, let's look at this frequency distribution, which shows the distribution of the weights of several men. So we went out and we recorded the weights of about 50 or so different men, and these weights fall into these different categories here. Now this first category says weights around 120. The second is weights around 135, and then around 150, and so on and so forth. So we don't give real precise descriptions of our different categories here. We'll just take them to be around these different numbers. And so here we've got some frequencies, or our frequencies of our data. So we had one guy in our sample that weighed about 120 pounds, about 4 guys weighed about 135, 7 guys weighed about 150 pounds, so on and so forth. And so what we want to do here is look at the pattern of these frequencies. And what we want to note here is that the frequencies start low, and then they increase to maximum here of 9, and then they start to decrease down to a low again. So we have this pattern, low, high, back to low, and this distribution is quote-unquote symmetric, meaning we've got roughly the same number of categories below the max as we do above the max. If we were to draw a histogram of this distribution, here's what it looked like. Now, this histogram is drawn using a different program than Excel, but that's okay. So we see here one bar for each of our categories. They start at a low, or they start short, they increase to a max, and then they decrease down to a low again. And we've got roughly the same number of bars to the left of the high point as we do to the right. And so whenever we see a shape like this, we say that this data has a so-called normal distribution. Normal distributions we're going to talk more about in next chapter, and we're going to see this idea of normal distributions come up later on in the semester as well. Okay. And so one thing we can do to illustrate this normal distribution pattern is to draw kind of a smooth curve that captures the general shape of this histogram. So this curve here starts low, increases to a max, and then decreases down to a low again. And this curve is what we call the bell curve. And this bell curve we're going to talk more about in next chapter.